Oh.
I will start the recording now. Let me know if I should pause it.
Mm. Oh, sorry. Oh, very loud. Hey, go. Hey. We'll start at 9 sharp, right?
Yes.
You don't need to wait anyone.
If it might be okay with the speakers, maybe we can wait a few minutes. It could be someone's setting up their Zoom session or so.
Okay. Okay, shall we wait a couple minutes?
I would be in favor.
Sorry?
I would be in favor of waiting 2 to 3 minutes.
Okay. Okay, we'll just wait 3 minutes and then we start. Okay, cool. Okay, two. Okay. Yeah, okay. We can start now. Wait, okay, cool.
Hello everyone, welcome to OpenEyes workshop at ECCB 2020. I'm Hyungjin Chang, one of the workshop organizers. The eye gaze modality is very informative in several application contexts, in particular, as an input method for assistive technology, and gaming, for measuring attention on user interfaces and advertisements, and for training pilots and operators in cockpits, or for monitoring vehicle drivers. Measuring human gaze and understanding it are both highly challenging tasks. The measuring of human gaze has had a long history. For example, the seminal work by Yarbus was carried out in the 50s. Though, as you can see, the measuring apparatus was complex and somewhat invasive. Newer solutions are significantly less invasive, using high-resolution machine vision cameras and infrared illuminators. More recent trends are attempting to bring the measuring and analysis of eye gaze outside of the lab. For example, mobile head-mounted eye trackers allow for analyzing consumer behavior, for example, in supermarkets. Light field-based methods in devices such as the Oculus Rift allow for foveated rendering in VR. And monocular methods such as open gaze allow for in-the-wild gaze estimation. All such novel methods are leading towards the next generation of immersive technologies. As such, there's a fast-growing interest in improving the state-of-the-art for eye gaze technology. It is truly an exciting time for researchers, practitioners, and industry players alike. Open forums of discussion provide opportunities to further improve eye tracking technologies, especially in areas like scale and generalization challenges in the next generation of AR and VR systems. For that reason, at the ICCB 2019, GAZE committee organized the first workshop titled Gaze Estimation and Prediction in the Wild, and independently, Facebook organized the first challenge, Eye Tracking for VR and AR. For 2020, the GAZE committees and Facebook are partnering to host a joint workshop titled Eye Gaze in VR, AR, and in the Wild at the ECCV conference. There are many outstanding and hardworking organizers made this workshop possible from various organizations in OpenEyes 2020. But organizing OpenEyes is not just by these organizers. We have to rely on a number of program committees that I'm going to list right in front of you. We thank all our program committees for their time and care in reviewing the submissions. Their efforts made this workshop keep in a high quality. Also, we have 3 industry partners that provide award prize or financial support to our workshop. We thank all their generous support. Their sponsoring makes the workshop shines. Today in OpenEyes 2020, we have 6 invited keynote talks, 4 accepted paper presentations by authors, and 2 challenge winner talks. This year, we were very fortunate to have outstanding 6 keynotes. I'm pleased to announce that this year's OpenEyes Work Best Paper Awards goes to Efficiency in Real-Time Webcam Gaze Tracking by Amo Goody, Jinlin, and John Van Gemert. Please join me in congratulating them. This award's prize is Titan RTX, sponsored by NVIDIA. Not only to the Best Paper Award, all the accepted papers will have one eye tracker sponsored by Tobii as prize. OpenEDS Challenge winners to be announced during the OpenEDS 2020 Challenge talk. This award is sponsored by Facebook. This is the schedule of today. Considering the time differences from all over the globe, we divided the workshop into 2 live sessions and put 8 hours separation in order to guarantee fair access from any time zone. In the first session, right after this opening remark, 2 keynote talks will follow. At the end of each talk, there will be live 5-minute interactive Q&A session with the speaker. After the 2 keynote talks, there will be full workshop paper presentations, 15 minutes each. After the paper presentations, Sachin Talathi from Facebook will introduce their hosting OpenEDS 2020 challenge, and challenge winner talks will follow. In the second session, 4 keynote talks are going to be given, same as the first session's keynote talks. There will be live interactive Q&A session for each. We hope you enjoyed virtual OpenEyes 2020. Thank you.
Great, then great. And Hongjin, please take in charge of all this. Yeah.
Okay, thank you, Chung. So it is truly fascinating that today we will have amazing 6 invited keynote talks today. Let me introduce our first speaker, Professor Ankeleda Kasneci. She is a professor of computer science at the University of Tübingen, Germany, where she leads the Human-Computer Interaction Lab. As a Bosch Scholar, she received her Master of Science degree in Computer Science from the University of Stuttgart in 2007. In 2013, she received her PhD in Computer Science from the University of Tübingen. For her PhD research, she was awarded the Research Prize of the Federation Südwestmetall in 2014. From 2013 to 2015, she was a postdoctoral researcher and a Margaret von Renge Fellow at the University of Tübingen. Her research evolves around the application of machine learning from intelligent and perceptual human-computer interaction. So today, Professor Kasneci will give a talk entitled as Eye Tracking, Ready to Deliver the Promises. So let's give a warm welcome to our special speaker. So please start.
Thank you very much. Hello, everybody. From my side, the talk will be recorded just to make sure that the kids are not here around disturbing during the talk. So enjoy the talk, and then I'll be afterwards available for questions. Thanks. Okay, so there's some questions here. So some people have written me privately in the chat during the talk. So
okay.
Questions have been answered this way, but for some of those was not even quick enough in responding. So if you guys, I mean, first of all, there was some echo in the talk, and if the quality was not perfect, I'm aware of this, but if you want to see any of these examples and really nice working videos, or if you want to have code sent to you or whatever, so we're still in the process of building up our web page, so you will not find everything there, but just shoot me an email and then we'll get this done. Okay, so one of the questions that people asked during, so in the private chat, and I see it also here with the CPF Google detection, is that, all right, so we have worked a lot on the head-mounted area, and I specifically looked at this because there's going to be a lot of talks also addressing the VR and AR setting, so it is all head-worn. scenarios, right? So, and I've shown here that if we actually try to improve the accuracies of the, or if you try to improve the quality of the eye-related features, you will even be able to look at those as proxies to cognitive aspects, and that's why we want to use eye tracking as well, right, to infer emotional cognitive conditions of people. And now we have done some of the evaluations on also other data sets, like not head-worn data sets, and I can send around some evaluations on this. So for example, like CBF with webcam eye images, which is another use case, right? Because that's like another domain in the work that we've been doing. We have infrared material, so infrared images of the eye. And then using with webcam, we will have to see how it performs. So we'll definitely not work like, will not work like as it is the code, but we will have to do some adaptations to make it run for RGB images. And but I would be very glad to look at it in a collaboration if anyone likes to send around some images or a data set that has been annotated that we can validate and evaluate the algorithms on it as well. So just if you're interested in this, just send me an email and we can have another Zoom call or whatever in this issue. So in the Q&A chat window was not used. So basically people use the chat window or wrote me privately. I don't know if it even works, but might be interesting also for the others to see the questions, right? So probably for the next talk, it'd be better to use the Q&A session. I don't know, I can see it here, but I don't know if the people can see this Q&A window.
I think the audience can see the Q&A.
Okay.
Yeah.
I just wanted to point out that with the Q&A, I was not able to find a way to ask a question there. That's why I put it in the chat. Maybe it's because I'm also a co-host. I'm not sure.
Oh, also not sure. Okay. Any question from the audience? Okay, there are no questions. Yeah, let's thank Ajalita again.
Thank you very much. And yeah, so I hope we stay in touch, right?
Yeah.
So looking forward to Mohammed's talk now.
Yeah. Okay. Hunjin, do you want?
Okay. Thank you for the talk. So our next speaker is Dr. Mohammed Khamis. So Mohammed Khamis is a lecturer at the University of Glasgow in the UK, where he leads a research team in human-centered security. He received his PhD from Ludwig Maximilian University of Munich. His research is at the intersection of ubiquitous computing and user privacy. He's interested in understanding the privacy implications of ubiquitous technologies, as well as developing novel systems for protecting privacy and security. So he has major contributions at the intersection of security and gaze. So today, Dr. Khamis will give a talk entitled as the interplay between privacy, security, and eye tracking in the wild, opportunities and challenges. Let's welcome him with our virtual big hands. Please start.
Hello, everyone. Thank you all for joining us today, and thank you to the workshop organizers for inviting me to deliver this talk. And my name is Mohammed. To use to an extent that it allows untrained people to even use it to maliciously to invade people's privacy, as we've just seen in the video. And actually, another example of a ubiquitous technology that could be used maliciously is eye tracking. So now we have eye trackers, they are becoming more pervasive than before. We have them integrated in laptops today. There are a lot of open source libraries for accurate eye tracking using RGB cameras that are integrated in laptops and the ones we use for webcams and so on. Also, mobile devices are actually developing so fast, and now you have a lot of smartphones that come with depth cameras or depth front-facing cameras, and these are very good for eye tracking, actually. So there are already a lot of applications online of sample applications that use eye tracking or do eye tracking actually on mobile devices such as the iPhone and Huawei and Samsung phones, so the recent ones that come with front depth cameras. And if you look into research activities, you can find even more, examples of pervasive eye tracking. So this is work that we did back in 2017, where we wanted people to interact with large displays in public areas. And we thought that we could move the eye tracker to allow people to interact while they are moving in front of a display. And then we took it further in another fun project where we used a drone to detect gaze gestures to the left and to the right and communicating this to a display. And this is all exciting, and brings, interesting opportunities of interaction in public space. But then actually, do we want drones around us that are tracking our eyes? Similarly, if you look at mobile devices, you will see that, there has been almost an exponential increase in the number of papers in the past years that propose using eye tracking, or they leverage eye tracking on mobile devices. The orange line over here shows papers that used eye tracking on unmodified mobile devices. So basically, just by installing an app, doing modifications on the software side, and that was even before the release of mobile phones that come with depth imaging, or at least depth imaging in the front-facing camera. So actually, we are starting to see more and more applications of eye tracking that are becoming more pervasive, that do not require additional hardware. And I agree that this is super exciting, but at the same time, it comes with privacy implications. So what are the privacy implications of eye tracking in the wild? What are similar things that could happen, things that are similar to the video that I showed you about thermal imaging? So if you look into research in psychology and other fields like neuroscience and so on, you can find that a lot of personal, like a wide range of personal information can be inferred from gaze data. So for example, some of the big 5 personality traits could be inferred from gaze behavior. You can detect emotional valence and cognitive states of users from their eye movements. You can also detect if a user is in a mind-wandering state, and probably the easiest thing you could do is that you could detect the visual interests of people using eye tracking. So actually, there was a paper from Liebling and Preibusch, I hope I'm pronouncing their names correctly. It was from 2014 called Privacy Considerations for Pervasive Eye Tracking World. And they list a number of things that could be detected from eye movements. And some of them are really personal information. So some things are age, gender, you might not want to share them with, the developer of a mobile app that uses eye tracking, but it seems that you could you can infer that from eye tracking data. You can even infer things like the effect and sexual preferences and hormonal cycles, which are really private things, and health even, like health issues. So this brings a lot of concerns, actually. And now, how could actually these attacks happen? So the users can be the victims. The users of eye tracking technologies could be the victims of these attacks. So when they're using eye tracking applications that are abusing the collected data, or they're collecting more gaze data than they need. So when I say data here, I'm referring to gaze data. For example, let's say a mobile application has access to the phone's camera and collect gaze data. And right now, there's no way to make sure the mobile app is using the collected data responsibly. If a mobile app allows the user to provide input using eye gaze, then it should actually just collect the information that allows interaction to happen and process it on the fly. The data should remain on the phone. It should not be sent to remote servers, for example, or it should not be stored beyond the duration in which it is needed. So it's important to also keep in mind here that people or developers might collect sensitive gaze data intentionally or unintentionally. So it could also happen unintentionally. They might, someone might just collect more data than they need, thinking that, okay, maybe it doesn't hurt. But actually, if you're sending this data to a remote server, if you're storing it on the phone, you're increasing the risk that someone might access it and infer private information about the user. Alternatively, what could happen is that the person that is using an eye tracker in a public area may actually infer personal information about people around them without their consent. So in an extreme example, imagine if I'm holding a mobile device that can track eyes, and I try to track the eyes of the person sitting next to me, and I can imagine that in the future you would be able to infer the private information that we've just looked at now in the previous slides. So if this was done previously on desktop computers, it'll tomorrow be done on mobile devices, or in the desktop computers or laptops that are being used outdoors, for example, or displays that are in public spaces that are coupled with cameras for eye tracking. These could all be problems that happen. So this type of this category of threats are fueled by the ubiquity of eye trackers and the wide range of sensitive information that could be inferred from them. So what I'm encouraging the eye tracking in the wild community to consider are to ask these questions. So what are the privacy implications of eye tracking? And how can we make eye tracking privacy aware? And how can we ensure the ethical use of eye tracking? So my aim here is just to highlight that researchers need to address the privacy implications of eye tracking before it's too late. And when I say too late, I mean that by late, I mean that everyone has access to this technology and could use it in a bad or a good way. So this is a call out to the community that works in eye tracking in the wild to start putting these questions into consideration. And the last question I have here is, how can we protect the privacy of users and everyone in their tracking range? So there has been some efforts in this area, actually, and I'll show you a slide in a second about differential privacy and so on. And there's also a number of researchers from eye tracking, from legal studies and law, and people from companies as well that are interested in this. And if you'd like to get in touch with this consortium, I'm happy to introduce you. So I discussed these problems in two recent papers, one in Mobile HCI 2018 and the other in CHI 2020. So if you'd like to start looking into this area, I advise you to start by those papers where we discuss the privacy implications of eye tracking in some parts of them and what are ways forward to address them. And some of the very promising work from recent research in this area is the work on differential privacy in eye tracking, and that was in ETRA 2019. So these two papers looked into using differential privacy for eye tracking data. Differential privacy means basically the idea of, imagine you have a data set of eye tracking data from multiple people. What you want to do now is that you want to make sure that you're unable to track the data back to the user or to the person from which this data was collected. But at the same time, you do not want to limit the utility of the gaze data. So balancing this is challenging. The concept of differential privacy is common in security, and these papers were among the first to apply this on eye tracking data, and there's also positive. And I think we need to do more work like that. We need to look more into how to protect privacy because we want to really benefit and leverage the eye tracking technology and do all the great things that we can that can be done with eye tracking. But in order to leverage this, we need to really be careful about privacy and the ethical things that could go wrong if gaze data is not used responsibly. So I think it's our responsibility as researchers to tackle this and ensure that eye tracking can be used in an ethical way. So I know this all sounds dystopian so far. As I said, don't get me wrong. I'm here to encourage. I'm a proponent of eye tracking, actually, and I know that it enables a lot of amazing things. I consider myself an eye tracking researcher. And actually, also in this direction, I'll actually now take a turn in the talk, and I'll tell you more now about how eye tracking can be used to improve privacy and security. So far we've been talking about how eye tracking as a threat to privacy, but then now can we actually use eye tracking to improve security and privacy? And the answer is yes, and there's actually a lot of interesting work in this area. So I think one of the earliest works in this area is the work by Kumar et al. Called iPassword, which in this work, it was published in the Symposium on Use of Privacy and Security in 2007. And basically, the idea was that you would enter passwords by using eye movements and dwell time to select keys on a on-screen keyboard. And the idea is that by doing this, it's harder for people around you to know what kind of password you're entering. So actually, security researchers were among the earliest adopters of eye tracking, and there has been actually there's a lot of earlier work than that about biometric authentication using eye gaze. So how to use eye movements to determine to distinguish users based on their unique eye movements. And actually, in the past couple of years, there has been an increasing use of eye tracking in security applications. So here, this is a figure that shows the number of papers published every year about eye tracking in security applications. And the blue ones are the ones that involve authentication. So authentication using eye gaze, be it biometric authentication or password-based authentication or knowledge-based authentication. So you can see that the vast majority is actually in gaze-based authentication, but there are also other categories, which I'll talk about in a bit, like privacy protection using eye gaze and also improving security based on gaze behavior. But the point I want to highlight here is that there has been an increasing use of eye tracking in security applications. And this is a positive thing. I think that there's a lot that could be done with eye tracking to improve security. So the following couple of slides are actually based on this paper called The Role of Eye Gaze in Security and Privacy Applications. Yeah, you can find more details there if you want to learn more about this. So we can roughly classify applications of eye tracking in security into three categories. There's authentication, there's privacy protection, and improving security based on gaze behavior. We can further split them to further categories, such as explicit authentication, where by this we mean like trying to intentionally move your eyes to provide a password. And there's implicit authentication or biometric authentication. I mean, another way to call it is biometric authentication. And there's the use of eye gaze to support multi-factor authentication. I'll speak in more details about explicit authentication today. And we'll also look a bit into privacy and so on. But actually, as I said earlier, there's the vast majority of the work done is in authentication, which is actually also, as I will say later, it's an opportunity for researchers to dig deeper and to look more into, how can we protect privacy using eye tracking and how can we improve security based on gaze behavior, because there is much less done in this area. And I think it's a shame because there's a lot of opportunities in there. So let's briefly talk about authentication first. So as I said, it can be split into these three categories. I'll talk about explicit authentication first. And now the nice thing about explicit authentication using eye gaze is that you could actually enter passwords using eye gaze in two ways. You could use eye gaze to enter what I call legacy passwords, or passwords password types that are already out there or that already exist. So for example, you use your eye movements to enter pins. And then there's gaze-based passwords where actually the password itself is composed of eye gaze movements. So let's see some examples. So on the left here, you see an example of a legacy password. So what happens here, the interface, this is a system called QAuth. What happens here is that the user is shown tiles or like keys similar to a pin pad. And then there is a moving digit in each of those boxes. And each one is moving in a unique way. And depending on how the user's eyes are moving, we correlate their eye movement to the movements of the objects on the screen. So basically, the user performs a smooth pursuit eye movement to follow one of these objects, and we compare this movement to the movement of the objects on the screen, and this tells us which object they're looking at. This way, actually, they're entering pins that at the end, they consist of digits, right? So they're only using gaze to select pins, basically. So the advantage of this concept is that, and any concept based, not just this system, this is just an example, but I mean the advantage of any gaze-based authentication system that uses legacy passwords is that it's very easy to integrate this into existing backends. So for example, let's say you have an ATM and you want to allow people to enter their PINs using eye gaze, which would be a very good idea nowadays, actually, with the COVID-19 situation, because you don't want to touch the screen that has been touched by dozens of people before you. So imagine that you want to enter a password using eye gaze. What we need basically there is an eye tracker and basically just an interface. We just need to modify the interface basically. But at the end, the PIN or the outcome, is what this system produces is a PIN or a 4-digit PIN, which could then be provided to the same backend. So you don't need to modify the backend of the ATM system or so. And that was the legacy type passwords. So the advantage is that they can be integrated easily, but a disadvantage, of course, is that people have to learn the mapping between the eye movements and the pins. So there are pros and cons. Now, the gaze-based passwords are the ones where the password itself consists of eye movements. And this is also very interesting because what you could do here in this example here, what happens is that the user enters a password on a mobile device that is composed of eye movements and touch input. So the user gazes to the left and then touches 1, and gazes to the right and then touches 4. So the password is left 1, right 4. It could be also different things like, it could be completely made up of gaze movements, or you could have more eye movements than touch input, or the other way around. But the point here basically is that the password consists of eye movements. And this is different in a way because it actually expands the password space a bit, because it incorporates new sets of password symbols. So now you don't only have digits from 0 to 9, but you also have eye movements, in this case here, left and right. So you have more options to make up your password, and this makes it more secure, or at least it makes the password space larger. On the downside, it might have a steeper learning curve because people are not used to entering passwords using their eyes. And this is actually here an opportunity or a research opportunity for people who work in eye tracking in the wild, because most of the I say most, but let's say the vast majority actually, or like almost all of the studies that involved gaze-based authentication, they were done in the lab. And the reason they were done in the lab is that we didn't have the hardware that allows us to take these concepts to the wild, right? So we didn't have the hardware that we have nowadays, like like mobile devices that can do accurate eye tracking. We didn't have those to allow people to use a method such as the one shown here for like 2 or 3 weeks in their daily lives. So we don't know how people actually select and recall gaze-based passwords. When you enter pins on a touch screen or a keypad, there is muscle memory involved. You start to remember how to enter your password. We don't know if this is if people also kind of have an equivalent of a muscle memory for their eye movements. So there are a lot of things that could be uncovered by doing an in-the-wild study of recalling gaze-based passwords in the wild, or selecting them or creating them and so on. And I know that today there are a lot of people also interested in VR, so I thought of bringing in a VR example, or an example of authentication using gaze in VR. What happens here is that a user enters a PIN in VR, and as you can see, if you look at this guy over here, you can see why this is a bad idea, because just from the movements you can tell that they're entering 1 because they're pointing at the top left, and then 9 because they're pointing at the bottom right, and so on. And now, luckily, many head-mounted displays that are used for VR and AR, they come with integrated eye trackers, and we're going to see more of those in the future as well. And this could be a nice way for authentication. So in this system over here, you are entering a password by looking at virtual objects in virtual reality and using this to authenticate, basically. A further way to categorize explicit authentication is based on the number of modalities involved. And so the typical thing is to use a single modality, or I mean typical, but I mean let's say the initial attempts for gaze-based authentication, people looked into using eyes or gaze as the only modality for entering passwords, like the systems here. So iPin responded to dwell time, and here you basically performed patterns using your eye movements. But then actually you could use eye gaze together with another input modality, like the example we saw earlier, actually. And there has been some work about that. There are very nice ways you can improve authentication schemes by combining multiple modalities. And eye gaze is particularly helpful here. So once you've built an authentication scheme using eye gaze, it's time to evaluate it, right? So usually you try to evaluate the usability and the security of the scheme. So when evaluating the usability, it's important to look into efficiency. So how fast do people enter passwords, efficacy, how many errors do they do, and also things like learnability and the user preference. It's very important to actually pay attention to usability because, you know, if you have a more secure mechanism and you want to use it to replace an existing one, if the existing less secure method takes 1 second to like people who use it would need only 1 second to authenticate, but your more secure method takes 6 seconds instead, so 5 seconds more. Now 5 seconds of additional authentication time on your mobile phone, for example. By the way, you unlock your phone about 40 to 50 times a day. That's what research tells us. So if you actually unlock your phone 40 times a day and you introduced 5 seconds to each authentication attempt, then you've added 200 seconds a day. If you do the math, it'll be like 20 hours a year of authenticating. If you do this in a lifespan, or if you do this for 60 years, then you have spent 50 days of your life unlocking your phone 24/7. So it's really important to actually improve usability, because if you introduce a very secure method that no one can use or no one is willing to use, then you haven't, or people, or worse, even worse, people are misusing it, then security is eventually reduced. And then there's security, which you can evaluate as well. And one of the things you can evaluate is the password space. The theoretical password space of authentication method tells us how many passwords can be created using this scheme. But other than the theoretical password space, there is actually the practical password space, which is how much of the theoretical password space are people actually using. And this could be different, could be drastically different, actually. So actually, here is another research direction as well for people working in eye tracking in the wild, because again, as I said, we have not done in the wild studies of authentication using eye gaze. And by doing a study like that, we can then see which kind of passwords people create and infer what the practical password space is. So this is something that is not yet investigated and not yet known, and it would be an opportunity for future work. So I've spoken so far about authentication. There's also privacy protection, which I'll talk about briefly. So you can use eye gaze to protect privacy by building applications that are privacy aware. So for example, there are some applications about transferring content from public displays to personal devices. And let's say you have a display in a public area that displays some news, and you want to grab some of this news and display it on your mobile phone, or just store it on your mobile phone. If you do this using eye gaze, then people around you are not aware of which articles you're interested in, for example, because people cannot easily map your eye movements to positions on the screen. So this was a paper from CHI 2018 where we compared eye gaze and touch and mid-air gestures to transfer content from the display to your phone. And people actually preferred the eye gaze method because it's private, right? Because people around them would not know which things they are interested in, which news articles or whatever they're grabbing from the screen, what are they interested in. You could also use eye gaze to do things like voting in public space, which allows you to vote, without, or select things without people around you figuring out what you've selected. So there is privacy and there is additional privacy in just using eye gaze as an interaction modality. And now this system over here called EyeSpot is also a way to protect privacy using eye gaze. What we did here is that we used an external eye tracker to tell where the user is looking on the screen of a mobile phone. And then we distorted the content around the point that the user is looking at. And this way, it limits the amount of information that bystanders have access to improve privacy of it. And we've used it using an external eye tracker, but I think with today's phones we can actually do this now using using the front-facing camera of a mobile device. We have not done that, but I think it's now feasible. And the last category is improving security based on gaze behavior. And what I mean by this is actually just tracking the user's eye gaze behavior. You can understand things about their response to security indicators on websites. You can spot if they have looked at the URLs or the senders of emails before opening them, and this could help you in detecting phishing attacks, for example, or warning people about phishing attacks. You can also do things like, for example, now you can create picture-based passwords on Windows 10 and so on, and people tend to select the same points over and over different people tend to select the same points for their passwords. And there was this work by Bulling et al. That used saliency maths to determine which are the points that attract attention the most and prevent users from selecting these points, because these are the points that are more predictable to be used as parts of your password. So by doing this, you're improving security, because people would then be forced to select more secure or unpredictable points for their password. And there has been a lot of work also by Cazzini et al. On creating user models for when people are creating passwords based on the eye movements, and using this to nudge them to create stronger passwords, or for example, detect or predicting which type of passwords they would create, and through their eye movements, whether predicting that they're strong or weak, and encouraging them in one direction or the other. So what are the main takeaways here? So gaze is very promising for security applications. There are applications of security in authentication and privacy protection, and in improving security based on gaze behavior. There's a lot to be done, especially in the last two areas, which are relatively under-investigated, which are privacy protection and improving of security based on gaze behavior. It's also now is the time to study gaze-based security applications in the wild. So this was not done in the past, and now we have the hardware and the computing power to do that, and algorithms and so on that allow us to do this. So there's a lot to explore, a lot to learn. This is what I mentioned earlier, that there is relatively less work on these two application areas, so we could do more there. And finally, what I brought up in the beginning is that the ubiquity of eye tracking can in itself be a threat to privacy, and this threat is relatively under-investigated. So, for example, we need to investigate if we can somehow ensure that gaze data that is collected through eye tracking apps cannot be used maliciously. So we are not able to do eye tracking on mobile devices, and we should actually ensure that in the future this is not maliciously used, either intentionally or unintentionally, by the users or by developers of mobile apps. So I encourage you all to join me in working in this area as well. Thank you very much, and I'm looking forward to the discussion session.
Okay, thank you very much for the interesting talk, Mohammed. Very nice. Yes, so is that any question from audience? You can post to the chat channel, or you can raise your hand, and then I will let you talk. Before that, I have one question for Mohammed. Maybe I missed it from your talk, but do you ever thought about to use the smooth pursuit as a password instead of tapping on the keyboard?
Yeah, so we've built some applications or authentication methods that use smooth pursuit for authentication. So in general, it works well, and it's also smooth pursuit in general is very good for interacting with displays and opportunities where you cannot afford asking the user to calibrate. So for example, if you're interacting with a public display, or also on a mobile device where calibration might not be very like the accuracy might not be very good. So the only problem with smooth pursuit and authentication is that it takes too long usually to enter a password, and I think this could be improved over time by like improving the detection algorithms. But so far in my experience, it's been taking slightly too long to enter a password, and if it takes too long to, you heard the example I mentioned earlier about introducing a method that takes too long. So this could have an adverse effect on security as well. Yeah, so in general, it's a very promising direction. Yeah.
Okay, thanks.
Thank you.
Okay.
So I think there was another question.
Okay, Shenwu have one question, yeah, in the chat.
Yeah, thanks a lot for the alternative take. It was a great talk, and I think it's really nice for people who also work on lower level, let's say, algorithms to see these perspectives. It's very optimistic, and I love it. The question I have is, as someone who has been working on or has does work on improving gaze estimation accuracy in particular, when are we ready, kind of? What's the kind of errors that make these kind of applications more tenable? What do you expect from your experience with mobile devices, in particular mobile phones? How good do we have to make these algorithms in terms of accuracy, head pose robustness, environmental effects, like lighting issues and so forth?
So yeah, if we speak about mobile devices in particular, I think, yeah, as you said, there are challenges in like lighting and also like, you know, obstacles as well, which could be things like the user's clothing, for example, or accessories they're wearing or so. Also the shaky environment in which the user is holding the phone. So if you calibrate once, it's probably you know, the calibration obsolete in a bit unless you actually involve the sensors of the phone to see how much it moved and try to compensate for that. So it's really, there's a lot of challenges in there, but I think you can do a lot by, if you focus more on gaze behaviors rather than, you know, estimating the like, you know, the gaze point precisely. So things like detecting gaze gestures or smooth pursuits, you don't really need very accurate gaze data to detect these types of eye movements. So I think they would work particularly well in compared to other methods, compared to, for example, dwell time on mobile devices. So I think that this direction would be more promising. At the moment, you would find like so when you ask like when will we be there, I think we're there already. It's just that we haven't done that much work on doing like eye tracking applications in the wild that are used for a long time on mobile devices, and I think we could uncover lots of problems there and opportunities to improve things. One thing, for example, is that there has been a recent focus on estimating gaze based on, you know, having a full face visible, and this is not always the case. So in a recent study, we found that in the vast majority of cases, like, and only 1/3 of the cases actually the full face is visible. So, but there are actually gaze estimation methods that just rely on just the eye patches basically to detect where the user is looking, and I think we should put more effort in this direction as well, because when using your phone in public space, you're holding the phone in a different way and you're moving and so on. So it's very unlikely that the full face is visible. So these are just different types of challenges that are compared to what we see in desktop settings.
Yeah, thank you very much.
Sure. So I can see a question here. So can you comment on the state of using eye gaze for authentication versus other well-established methods with respect to accuracy and false positive rates? And one more question, what about fast eye movements? So I think it's hard to make a general comparison between using eye gaze for authentication versus other methods, because it depends at the end on how you use the user's gaze. So if you do something like, you know, an interface that reacts to users like dwell, like on basically dwell-based interaction or dwell durations, then it's more likely to take longer actually for people to enter passwords. In terms of accuracy, it also depends on, for example, things like there are like environmental factors. There are, if we're talking about mobile phones, there's like shaky environments and so on. But in general, I think that you can do, you can perform better, like better than for example tactile input in terms of speed if we keep improving our eye tracking algorithms and also how fast we can detect them and so on. But I mean, it's difficult to make a general comparison. And also another thing to keep in mind is that people are already used to touch screens and tactile, keyboards and so on. So if you do any user studies, people are actually already biased because they're likely used more keyboards or more touch screens in their lives than they have used any eye trackers, right? Okay, well, the following question is, what about fast eye movements? I think you mean that whether like fast eye movements would actually cause problems when trying to authenticate because they're too fast to detect, or yes. So yeah, okay, so this is what you mean. Yes, so I think that this is also a problem. So I think it's a problem in general, like a general eye tracking problem, and not just an authentication application. But I would say it's even probably more frustrating if you're trying to improve privacy or security. So even like the example I mentioned about eye spot, where you move your eyes, where the area around the area around the place you're looking at is distorted. For example, imagine if this is not following up with your eye movements quick enough. This would be frustrating and probably would make people less likely to use the method. So it's an important thing to consider, and maybe to try to optimize for these situations to make sure that the usability is not deteriorated significantly. Because as I said, if the usability goes down, people are less likely to use the new secure, or the more secure, or the privacy aware methods. So yeah, I hope this answers the question. Okay, so afterwards there is a question about spoofing. So won't spoofing print attacks be a problem if we implement this application unlocking phone and all? So I'm not sure I get the question. So
it's also relative to the question in the Q&A, and how do you look at the level 3 attack, like how to check eye gaze estimator, like
okay,
attack.
Yeah. Well, we haven't looked into that, but there is actually work on trying to basically so actually, like if you record the user's eye movements, you could for example, let's take as an example an authentication method that uses eye gaze. If you record the user's eye movements, which is actually in some situations is easier than recording the input on the screen, you could then learn the password or the eye movements that they're providing or they're entering in order to enter the password. So this could be actually an additional attack vector. As for tricking gaze estimators, now I haven't done work in this area, but it's an interesting direction as well, because if you introduce a new way of entering passwords, there are then new types of attacks or new problems that could take place. But also, I mean, this could also happen in general, I guess, so not just with authentication. So, but I haven't done work in this area, so I don't have much to tell there. How could gaze estimation and eye tracking for security talking here be well used for driver monitor case? Okay, so the question is, if gaze estimation could be used, if gaze estimation for security could be used for driver monitoring situations. So I think there's a lot of like in the previous keynote, there's a lot of applications of eye gaze in monitoring monitoring drivers. In terms of security, I mean, to be honest, I haven't thought of using eye tracking for security applications in a driver situation. There may be interesting things to do there. Yeah, I guess probably you could think of ways to for example, verify your identity to the car, for example, through your biometric eye movement, through the behavior of your eye movements. So, for example, the car would know that you're the right person because you're moving your eyes the way you usually, like the driver of that car usually does. So this could be an interesting application there. I mean, if you think of non-driving cars, it could also be a way to identify which user is now in the car, and then, for example, based on that, load their favorite destinations, for example. So imagine if there's a non-driving taxi, for example, a taxi, for example, without a driver, and then once you get in, based on your eye movements, it could tell which person you are, and based on that, kind of giving you some options to choose from for your destinations and so on, based on your previous history. I guess there are other ways to do this as well, other than eye tracking, things like facial recognition and so on. But this is certainly also an interesting direction.
Okay, is any more question? I didn't see it. Okay, then let's thank Muhammad again for nice talk.
Thank you. Thank you for having me.
Okay, then we move to the next one, which is the Shinwo Park, please.
Yeah. We've had the great pleasure of having multiple submissions into our workshop this year. We were able to select 4 papers for acceptance and presentation. So these papers will be now presented in the order in the following manner. First, a talk by Amokuri, and then Yeju, Yerushan, and lastly, Jonathan Perry. I'll briefly introduce every talk in terms of title and presenters, and there will be a few minutes after every talk for a few questions to come. As before, you're very welcome to ask your questions in the Q&A box or in the chat box, preferably the Q&A box, and we will try to get through this. So first up, we have Amokuri, who will be presenting his work with his colleagues Xin Li and Jan van Gemert on efficiency in real-time webcam gaze tracking.
Morning, ECCV. My name is Amol Guri. I'm a research engineer at Vicker Vision, a computer vision AI company in Amsterdam, and I'm also a PhD student at TU Delft. On behalf of my co-authors Xin Li and Jan van Gemert, I'll be presenting our work on efficiency in real-time webcam gaze tracking. So here's a short introduction about what webcam gaze tracking actually is. The main goal is to estimate where a person is looking using only the images obtained from a webcam or a camera. The main use cases of such technologies can include UX studies or attention analytics, where we want to know where the user of a computer is looking at on the screen. So the typical settings of the use of such technology can include computer-facing scenarios, as I just mentioned, and usually no additional or specialized sensors are available. For example, no infrared cameras or no eye trackers. And a goal is to estimate point of gaze on the screen. So just estimating the gaze direction with respect to the head pose or the camera is not enough. And as a challenge to this, we don't have knowledge about webcam monitor placement. So this can make estimating gaze points harder. Here's an illustration of our webcam to screen gaze tracking pipeline. This pipeline takes camera images as input on one end and outputs the 2D gaze points on the screen. The first step in the pipeline is to perform face modeling to obtain key landmarks on the face. These landmarks can then be used to obtain normalized face or eye crops. The next step in the pipeline is a convolutional neural network, or a CNN, which is a type of deep learning architecture that is used to analyze images. The normalized face crops can then be used to train the CNN to estimate 3D gaze vectors. These directional vectors are with respect to the virtual face crop. However, because we know the transformation of obtaining these face crops, they can also be converted with respect to the person's head pose or with respect to the camera. Now, as mentioned before, what we really need are 2D gaze points on the screen where the person is looking at. In an ideal situation, we would know the exact physical relationships between the camera and the screen. For example, where the camera is placed with respect to the screen. However, in real-world situations, this relationship is usually not known. To roughly estimate this, we make use of user-assisted screen calibration techniques. These techniques essentially estimate the transformation parameters between the camera coordinate system and the screen coordinate system. Alternate ways of obtaining gaze points on screen could involve training or fine-tuning the CNN to directly predict the gaze points, or to extracting embeddings from the CNN and training a separate neural network to estimate the gaze points. However, in comparison, our screen calibration pipeline is more modular because it only depends on the output of the first part. And therefore, the whole first part of the pipeline could in theory be swapped out for something that is more accurate or can run faster. The main contributions of our work are as follows. We perform a study of efficiency of the different input types that could be used to predict the gaze vectors in terms of their accuracy versus computational load. We demonstrate 3 practical calibration techniques that can map gaze vectors onto points on screen. And we perform a usability efficiency study of these calibration methods to figure out how tedious or easy these methods are. For the study about different input types, we focus on 3 main input types. The first one would be the full face image. This image has the most amount of context required to estimate gaze vectors. For example, it doesn't just have the eye locations, but the whole face is visible to the CNN. Conversely, this input type also has the largest size. These are the 2 sizes we chose, 224 and 112 pixels. In addition, we also tried a smaller region of just the 2 eyes together. This has a lot less context than the previous input type, but also the size is a lot smaller. Finally, to test the smallest case, we also tried it with a single eye in 2 different sizes. This has the least amount of contextual information that is absolutely necessary to predict gaze. After all, gaze depends on the appearance of the eyes. For our study about the screen calibration techniques, we make a few assumptions to simplify the problem for us. First of all, we assume that the webcam is not tilted with respect to the screen. That is, the roll and yaw of the webcam with respect to the screen is fixed and known. This is a realistic assumption because, for example, most laptop webcams are built in, so it is not even possible to change the tilt with respect to the screen. And even external webcams are typically placed such that they are facing the front of the screen without any yaw changes. We also assume that the matrix parameters are known. In reality, even if they're not known, they can be roughly estimated. And finally, we also assume that the eye location is known with respect to the webcam. The rough eye location in reality is known because of the face modeling step, which can provide landmarks for the eyes. We study 3 types of calibration techniques in our work. The first one is calibration by geometry. This essentially involves estimating the rotation and translation matrices to figure out the transformation between the camera coordinate system and the screen coordinate system. The figures on the left demonstrate the camera and screen coordinate system links in this scenario. Calibration by geometry essentially imparts the maximum amount of prior knowledge into the calibration method because we give it all the relationships that we know of, all the geometric relationships that we know of. We also try calibration by machine learning. In contrast, this method utilizes the least amount of prior knowledge about the scenario. In this method, we simply feed as input the eye location and the gaze vector angles to the machine learning regression model, and we get as output directly the 2D points on the screen. So this model is trying to directly map the gaze vectors and the 2D points without any further input about the properties of this input or output. This method has to learn these relationships completely on its own based on the data fed. Finally, we also try a sort of hybrid geometric regression approach. This approach also involves estimating the rotation and translation matrices that was used in the calibration by geometry method. However, once all the calibration points are collected, we can train a regression model to minimize the reprojection error. This method also imparts a significant amount of prior knowledge into it, as it is aware of the geometric relationships. In addition, it also takes advantage of regression techniques' ability to learn. So this way, it can make use of multiple data points to learn all the missing variables within the rotation and translation matrix. The results of our experiments are as follows. For the speed versus accuracy trade-off experiment, we notice that the error doesn't really become a lot worse for using the smallest type of input available, that is a single eye image, in comparison with the largest type of input available, that is a full face image. Similar results were also obtained on both on the MPII face gaze dataset and on the IDApp dataset. This suggests that perhaps for gaze tracking, the use of extra contextual information is not that high or not that vital for the network. In terms of applications for real-time systems, this shows that if you are willing to lose a slight amount of accuracy, you can gain a lot in processing, a lot of savings in terms of processing time. So in this figure, you can see that these are the inputs that only use a single eye, and they are falling within the standard deviations of the other results, but they are much faster. In fact, this line represents 15 FPS performance on a i7 CPU. The results on the usability study of the screen calibration methods are as follows. If we were to evaluate on pure ground truth vectors instead of the predicted ones to simulate an idealized scenario, we notice that the hybrid geometric calibration technique performs better than both the purely geometric or the purely machine learning method in all scenarios. If we were to repeat this experiment for the predicted gaze vectors from our gaze estimation system, similar results were obtained, except in the moving head poses of the IDApp dataset. In this table, static refers to the static head poses of the IDApp dataset, and moving refers to the moving head poses of the IDApp dataset. In order to better study the usability trade-off for screen calibration methods, we can plot the learning curves of these methods. For example, here for the IDApp dataset, we see that when a very low number of calibration points are present, the machine learning method performs the worst, and the geometric method performs better than it. However, at some point, when enough calibration points become available, the machine learning method's performance dramatically improves, while the geometric method performance stagnates. The hybrid method performs better than the geometric and the machine learning method when medium to low calibration points are present. Only when calibration points become really abundant, the performance of the machine learning method becomes better. In realistic scenarios, something like 15 calibration points would be the case. The results on MPII phase gaze datasets are somewhat similar. However, in this case, the hybrid method always performs better than the machine learning method. From these results, we can gain some insights. The improvements from the large input sizes seems to be fairly small with respect to their very high computational load. So for real-time applications, a smaller input should be preferred. So this kind of raises a question about the role of context for gaze tracking, and it seems to be somewhat limited. Perhaps a different kind of context can be more useful than just a larger image. About the calibration methods, we could see that overall the hybrid geometric calibration method outperforms a purely geometric or purely machine learning calibration method. This probably says something about striking a balance between use of prior knowledge and model flexibility, because the geometric model was very rigid, while the machine learning model had no prior knowledge. For our future work, we plan to perform also a data efficiency study for the different input types. Small input types perhaps could take less data to train, but this would we need to find this out. And secondly, it would be useful to design the screen calibration methods with weaker assumptions. For example, what if a webcam is not even placed anywhere near the screen, but on the side? This would lead to a more generalizable calibration method. Thank you for your attention.
Okay, thanks. Good. Thanks for the good talk. And I'm over here. Oh, sorry.
Yes. So we're ready to accept some questions. Thank you for the very nice talk. I see now there's one question from Smriti Joshi, who's asking, could you account for challenges such as illumination and occlusions, and look into the accuracy of face detection in the case of appearance changes?
Right. Of course, changes in difficulties in illumination conditions and lighting conditions affect all the components within the pipeline. So also the face detection system, also the landmark detection system, and the gaze tracking itself. We didn't explicitly study this because we used publicly available data sets, which I think they did not have labels for this. Yeah, but it's a good research direction to explore the limitations of appearance-based gaze tracking methods.
I have one question. I first want to compliment you on this very creative use of your own face. I thought that was very nice. Made it very enjoyable.
Thanks. I tried to make it a bit funny.
Must have taken a while.
Yeah. Yeah.
What? I'd like to ask a question on a similar line as in the previous talk. And basically, so I've worked more on improving the benchmark essentially, and there small improvements matter a lot. And I was very intrigued by your characterization that using more context does not give much improvement. The y-axis that I, for instance, have looked at looks at a finer change in performance. And I was just wondering what your thoughts are there in terms of practicality. Is the performance degradation, justifiable, would you say, in terms of practical terms?
I would, of course, it depends on the application, but I would say so, yes, because actually the origins of this project was for the development of a webcam-based eye tracking system. So that was anyway the goal. And we wanted to make something that runs fast on a CPU and doesn't need a GPU. So in our observation, for us, it's already good enough if we can, for example, predict the right, let's say, area of I don't know, 5 centimeters by 5 centimeters, something like this, where the person is looking. It doesn't have to be pinpoint, at least for the applications we were interested in. And for that purpose, it works fine. But of course, if you want to enter your password through gaze, maybe then it could lead to challenges. Yeah.
I see. Thank you. Do we have any more questions from the audience? There was a compliment on the nice talk.
Great. Thank you.
All right. That does not seem to be the case. Do check out the paper and the talk on the OpenEyes website, where you can find the email of the authors.
Hello,
I'm sure
everyone.
they'd be happy if you... Okay. Thank you, Amo. For the next talk, we have Yezhu. Due to time zone difficulties, unfortunately, we couldn't accommodate everyone's time zone. Apologies for that. So the author is not present, but as mentioned, the email is available on the paper. The presentation is from Texas State University, and it is work between Yezhu, Yan, and Oleg Komogortsev. And we will now show you the presentation. Thank you.
Hello, everyone. I'm Yezhu from Texas State University. I'm going to present our work for the paper Hierarchical Hidden Markov Model for Eye Movement Classification. Eye tracking technology nowadays has attracted much research attention and interests, and it is becoming a potential and promising driver for future immersive technologies. One fundamental and significant research topic in eye tracking is to identify different types of eye movements. In this work, we tackle the problem of ternary eye movement classification, which aims to separate fixations, saccades, and smooth pursuits from the raw eye positional data. The existing work related to eye movement classification usually has two main branches. One focuses on the threshold-based algorithms using threshold values for features such as the velocity and dispersion. Another branch adopts more recent machine learning and deep learning techniques. For the threshold value-based algorithms, they usually require manually pre-selected threshold values to achieve good classification performance, which is kind of inconvenient. For machine learning, especially deep learning methods, they are becoming more popular due to its promising competence. However, these data-driven methods rely on a large amount of data for training the neural network, and when the task changes, the retraining process is needed for the network to achieve equally good performance for the novel task. Different from the existing work, we propose a statistical hierarchical hidden Markov model for detecting fixations, saccades, and smooth pursuits. The proposed algorithm leverages different features from the recorded raw eye tracking data with a hierarchical classification strategy, separating one type of eye movement each time. Our objective is to improve the robustness and performance of the threshold-based methods and even competing with more recent machine learning-based state-of-the-art methods. Now we start to present the methodology of our work. Hidden Markov model is a statistical model for time series based on the Markov process with hidden states. The principle of the hidden Markov model is to determine the hidden state with a maximum probability according to the observation sequence. Generally speaking, it relies on the distinguishable probability distributions of features to correctly define different hidden states. In the case of eye movement classification, the probability distributions for different movement types are usually represented by continuous Gaussian distributions. The main challenge of ternary eye movement classification using the existing methods lies in the biases of the features for smooth pursuits. While fixations and saccades have very different positional dispersion and velocity features, smooth pursuits are rather ambiguous in terms of dispersion and velocity, since the steady state of a smooth pursuit often contains corrective saccades, making the eye tracking data very noisy. Here is the pseudocode for our proposed hierarchical hidden Markov model algorithm. Firstly, we start by analyzing different features of the raw eye positional data as a pre-processing step. So the objective of the pre-processing is to determine the features that can be used to separate three eye movement types in later steps. In our case, we select the velocity and the positional features. After selecting appropriate features, we then perform the first stage rough classification on the eye tracking data to separate saccades from the fixations and smooth pursuits using the hidden Markov model. We refer the first stage as rough classification due to the reason that the classification results will be fine-tuned in later steps. The second stage classification adopts a different feature to separate fixations and smooth pursuits by another hidden Markov model, using the first feature as a fine-tuning criteria at the same time. The final step of our hierarchical hidden Markov model is to merge the classified points into complete eye movements with temporal and distance duration criteria. More implementation details can be found in our paper. Next, we continue to present the experimental part of this work. We use the eye tracking dataset recorded from the previous research work for experiments. 7 different behavior scores are used as quantitative evaluation matrix for our experiments. We compare our proposed hierarchical hidden Markov model with 6 other baselines: IVVT, IVDT, IVNP, IRF, IBDT, and 1D CNN with bidirectional LSTM. Among these 6 baselines, 3 of them are threshold-based methods, while others are learning-based. All the threshold values are optimized for different subject recordings in our experiments for comparison for the threshold-based methods. For other methods, we split the dataset recordings into training and testing splits. Among 11 recordings, 3 subject recordings are used for testing. Specifically for 1D CNN, we take the pre-trained model and fine-tune it on the training split of this dataset. In this table, we report the behavior scores obtained via the proposed method and other methods on the subjects that are manually evaluated as medium, good, and bad in the eye tracking data quality. The ideal scores and manually classification results are also reported for comparison. The calculation of the ideal behavior scores considers the actual physiological reactions of humans when performing different types of eye movements. We observe that our proposed method achieves promising performance compared to other baseline methods and is much closer to human performance. except for the IVVT that has difficulty in detecting the smooth pursuits. Other methods can more or less detect 3 different types of eye movements. For the threshold-based methods, IVNP has slightly better performance compared to IVDT. For the learning-based methods, the 1D CNN slightly underperforms than others. One possible reason for its underperformance could be the limited amount of smooth pursuit data for fine-tuning. Since the original model was trained in a different dataset and fine-tuned in our experiments, the transfer learning process may be less effective compared to retraining the entire network model, which also reveals one of the limitations about those data-driven methods. We then present the qualitative classification results in this figure. The qualitative results are consistent with the previous quantitative results. Notably, our proposed method succeeds in detecting an unexpected saccade, while most of the other methods detected either as smooth pursuit or fixation. We further conduct an additional ablation experiment to demonstrate the necessity and effectiveness of the proposed hierarchical structure. Since the fixations, saccades, and smooth pursuits can be considered as 3 hidden stages, we use the velocity feature as a criteria and adopt a single-stage hidden Markov model with the 3 hidden states to do the same task. In other words, we remove the second stage classification from the proposed model. The experimental results for ablation analysis prove that the hierarchical structure contributes to better classification results. In conclusion, we propose a hierarchical hidden Markov model algorithm to tackle the problem of ternary eye movement classification. Its core idea is simple yet effective. It avoids to manually select the threshold values and do not require a large amount of training data. A deeper hierarchical structure for more eye movement types could be a possible future direction for this work. Thank you for listening.
All right, thank you very much to the speaker. As mentioned, the speaker could not join us in live due to time zone difficulties, but please do reach out to her. You can find the link to the PDF of the papers as well as a recording of this talk on the website openeyes-workshop.github.io. Now we will move on to the next talk, which will be given by Yiru Shen from Facebook Reality Labs, which is work in collaboration with Oleg Komorodtsev. Apologies if I'm butchering that pronunciation, and Sachin Talati. This work is titled Domain Adaptation for Eye Segmentation.
Hi, I'm Yiru. In this talk, I'm going to present our work, Domain Adaptation for Eye Segmentation. This work is produced by eye tracking team from Facebook Reality Labs. Eye tracking is a critical field in the AR/VR community to capture and understand eye states. We need to develop robust eye tracking models for real-world applications, which can reliably work under all environmental conditions, across different hardware configurations, and work for all individuals. Recently, machine learning has been used to apply to various eye tracking applications. For example, in gaze tracking, we need to take eye images as input and train a segmentation network to produce the masks. Later on, a geometric model is used to map the masks to estimate gaze. In this case, we need a large amount of data and the corresponding annotations to train the eye segmentation network. However, data annotation is label expensive and time-consuming, especially for segmentation tasks where each pixel needs to be labeled. Therefore, domain adaptation has been applied to ease the problem of data annotation. Domain adaptation is the ability to apply a model trained in one source domain to a different but related target domain. Usually, we have one source domain where the quantity of data is usually large and the quality of annotations is guaranteed. And we have a target domain, where quantity and quality of annotations is limited. In this work, we use OpenEyes as a source domain data, which are collected in a lab-controlled setting. We collect eye images using a VR head-mounted device as a target domain data. As you can see, the varying illumination introduces challenges in the data, and quality of annotation is not guaranteed. For example, the corners of sclera is not captured in annotations. However, domain adaptation can't be naively used due to domain gaps between source and target. Here, we show an example of segmentation prediction from model which is trained on source domain data and applied on target domain. It's clearly that the poor performance is due to the domain gap between source and target data. Therefore, we need to carefully design the pipeline to drive the two distributions closer. Here, I'd like to mention the notations and goals of our work. In domain adaptation, 3 frameworks are mainly studied. Unsupervised domain adaptation, short for UDA, applies this for cases where no annotations are available in target domain. Supervised domain adaptation, short for SDA, is applied when limited label target data are available. And in semi-supervised domain adaptation, short for SSDA, in addition to a small amount of labeled target data, a big chunk of unlabeled data is available. We believe SSDA is more suitable for real-world scenarios, and in this work, we investigate SSDA by asking the following questions. Given a fixed annotation budget, how much data needs to be labeled to reach a reasonable performance on target domain? We systematically compare UDA, SDA, and SSDA performance as a function of the number of available target data during training. The second question is how to optimally utilize unlabeled data. We explore the semi-supervised learning to maximally leverage the information from unlabeled target data. Our pipeline consists of 2 subnetworks, a segmentation network and a discriminator. The discriminator is a fully convolutional neural network which takes probability maps from segmentation network and outputs a confidence map. This map indicates how confident the discriminator about each pixel in the image belonging to source or target domain. Here, we show the loss functions for these 3 frameworks. I'm not going too detailed, and please refer to the paper for more information. A bit more would be talked on how to utilize the unlabeled target images to improve segmentation performance. Specifically, a semi-supervised loss is designed by generating pseudo-labels for eye regions in the unlabeled target images. The discriminator generates confidence score for each pixel in the image belonging to the source or the target domain. Only the pseudo-labels of regions where the confidence score is above a threshold is used to train the segmentation network via a masked cross-entropy loss. Here comes the results. As mentioned before, we aim to investigate how the performance on segmentation is impacted by varying amounts of target domain data during training. Here, we show the performance of UDA, SDA, and SSDA trained with varying amounts of target data. We note that the mean intersection of union increase and reach a plateau as more target data are available, and the extent of increase is much smaller for model trained under UDA. With only 200 labeled target images, mean intersection of union is improved by 5.4% and 6.6% from UDA to SDA and SSDA, respectively. It affirms our hypothesis that, even with limited number of labeled target data, domain-specific information can boost the performance. SSDA consistently outperforms SDA, since it's able to leverage the most available information. The gain in the performance for SSDA relative to SDA is brought about by the addition of adversarial loss and the semi-supervised loss from unlabeled target data. However, since we have a fixed amount of target data, and in SSDA, as more target data with annotations are provided, the amount of unlabeled data is decreased. Therefore, the performance gain brought from unlabeled data is diminishing. This explains the smaller performance gap between SDA and SSDA as more labeled target data are available. Also note that SSDA is able to achieve a competitive of 89.5 with a round of only 50 of the data being used. It is encouraging to observe that the proposed SSDA can efficiently take advantage of insufficient labels while still producing competitive performance. We summarize the performance for the case when all the labeled target data are used. Note that the lowest accuracy is from sclera. However, for many eye tracking applications such as gaze estimation, more focus is on high accurate pupil segmentation, where SSDA could deliver up to 90% accuracy. Finally, we show some visualizations. Note the labels in target domain are missing fine-grained boundaries, such as detailed boundaries of sclera. Domain adaptation is able to transfer the knowledge from source domain with high-quality labels to target domain to improve segmenting detailed geometry, such as sclera in the target images. We also show the t-SNE visualization of 3 frameworks. Qualitative results show that with domain adaptation applied, the distributions of source and target domain overlap closely. As a takeaway, we consider the problem of domain adaptation for eye segmentation under the setting where a small amount of labeled images and a majority of unlabeled images in the target domain are available. We systematically compare the performance of eye segmentation models using UDA, SDA, and SSDA as a function of the number of labeled target data. Results demonstrate the benefit to annotate a small number of target domain data to effectively perform domain adaptation using SSDA. In our future work, we plan to explore what aspects of eye tracking data quality are affected by segmentation of paraocular regions. Thank you.
Thank you very much for the talk. All right. If you have any questions, the people in the audience, that is, please don't be shy. The author is here, so it'd be great if you can ask some questions. I can kick it off first. First of all, I think it's very, very interesting work.
Thank you.
Definitely reflects the real data situation, no matter what, actually, no matter only eye tracking or eye segmentation or so on. Mm-hmm. We will always have different data sets annotated slightly differently. One thing I was wondering is, I understand the carbuncle region is annotated differently, but I guess the rest is going to be relatively consistent across data sets, and whether some amount of training data augmentation might be able to tackle some of these discrepancies already. That's my question.
Okay, so I think it's a very good question. So what we're really interested in, as aligned with your question, is to which extent could work best in the real world scenario. So in the real world scenario, we not only have pool quality of the annotations, and also we have data sets which are collected in varying illuminations, so which are all covered in the data set. And so you're saying by using different kind of the data augmentation, somehow it will boost the performance. But again, we are thinking from the perspective of we only have very limited annotations. Also, the annotation is with poor quality. How would we transfer the knowledge from another similar but different data set to help with our case, like to, in the best case scenario, how to best solve the eye segmentation, where the data, like it contains a varying illumination and also the quality is not good, even like the quality from the data set and the quality from the annotations, they are limited. So again, like we have done some experiments, try to compare directly using the limited data to train the model with some augmentation. But it turns out that like the domain adaptation, it does improve the performance to a great extent. And also another situation is like in our current work, we're trying to explore this work frame into a broad field. Like we're more interested in like how to transfer the simulation data, which we have full controllability, to realistic data, which like the data amount is pretty large, but the quality is not very good, and also still we don't have enough annotations to train the network. And we will like answer more questions regarding the data augmentation, regarding the varying data quality, the varying amount of data annotations in our ongoing work. So yeah, thank you.
Yeah, thank you very much. In the meanwhile, I do have a follow-up, but I'll try to restrain from asking it yet. There has been one question from the audience. The Sanchit Hira asks, were there studies comparing target domain only model trainings with varying amounts of data and how they compare with domain adaptation? So I suppose, yeah.
Yeah, so that is another very good question too. So we did have some experiments to directly using the limited target domain data to compare with, so like in our case, the SSDA semi-supervised domain adaptation, it has the best performance. So we compare there with the fine tuning directly, sorry, it's not even the fine tuning. So there are different baselines. One baseline is from this question, like we directly train the target domain data with like directly train the segmentation network with the limited target domain data. And another baseline is like we train the segmentation network with a source domain, and then we fine tuning that with the limited target domain. And the third one is the SSDA. So with very limited data available in target domain, SSDA has the best, like the largest performance gain compared to the fine tuning and directly training the target domain. But we haven't done the experiments of varying the amount of data for only training this segmentation network on the target domain. But we do observe that like with limited target domain data, the SSDA has the best performance with more than 3% more intersection over union compared to the two baselines.
Thank you very much for your answer.
Yep. Another thing is like in the current presentation mode, it's not the original presentation mode. So like some of the images and the information they're being cutting off. So not sure like if we can share our slides later on, or like again, this talk is already available online. So feel free to check the original version of the video for the best quality.
Yes, in general to all the other authors as well, I very much welcome any additional links or materials, anything that would help expose, give better exposure for your work. And if everything is accessible from my website, hopefully it helps the community more. Okay, thank you very much for your time. I don't believe we have any further questions.
Thank you.
As with other speakers, please check the papers and the contact details there.
Bye.
Thanks. All right, so now we are at our last talk. The speaker is present. However, due to some technical difficulties, we may have to perform the Q&A over text. So even more so than before, please ask your questions a little bit in advance via the Q&A module. The talk is titled iSeg, Fast and Efficient Few-Shot Semantic Segmentation. And this is in relation to the OpenEyes challenge, which you will hear more about later. This work is by Jonathan Perry and Amanda Fernandez from the University of Texas at San Antonio.
Hello everyone, and thank you for taking the time to tune into this presentation. My name is Jonathan Perry, and I am a graduate student at the University of Texas, San Antonio. I'll be presenting ISEG, Fast and Efficient Few-Shot Semantic Segmentation. This work is authored by myself and Amanda Fernandez, my advisor and principal investigator at the Vision and Artificial Intelligence Lab here at UTSA. Before diving into this approach, I would like to mention that the order of this presentation may not be in the same order as it will appear in the paper. That being said, this presentation will cover the key points outlined before you, starting with outlining the challenge and the motivation for this work. I will cover related works and the contributions we provide with ISEG. Lastly, performance and results of our approach and planned future works. So if you are unfamiliar with the challenge, this challenge is the OpenEyes Dataset Sparse Semantic Segmentation Challenge. This is the second iteration of the OpenEDS challenges, where this one has a primary motivation focused around accessibility of large amounts of unlabeled data with very few manually labeled samples. As the title of the challenge suggests, this data is comprised of head-mounted display video recordings of the wearer's eye, provided in sets of sequences with only a few of the frames per sequence manually labeled. The labels are comprised of 4 different class features per sampler image. That's your background, your iris, your sclera, or your pupil. This data set does have roughly 29,000 images, and only 2,600 of those images are labeled, and 1,000 of which are within a hidden test set. So to mention some previous approaches to similar problems and methods, including UNet, which UNet contributed a network with skip connections or residual connections for maintaining high-level or simple features. Deep Lab showcased dilated convolutions where it expands the effective field of view for the convolutions. But more closely related to this approach are previous works produced through the first iteration of OpenEDS challenge, which showed very promising results leveraging neural networks focused on a low amount of parameters. RATNet applied adaptive histogram equalization, a varying data augmentation technique, and a combined loss function. MiniNet applied stack dilated layers into a encoder-decoder framework. So to go on to the ISEG framework, to take a high-level view of ISEG framework, specifically encoder-decoder framework, this network kept a consistent filter size throughout the entire network. As you can see, there's 4 encoder blocks and 4 decoder blocks. ISEG utilized residual connections within each block, and you can see that with those blue lines. This network was additionally built to be conscious of memory size to be employed on embedded systems for real-time environments. Being it's only 190,000 parameters, this can be considered a lightweight design and capable of that. To break down each of the types of blocks within ISEG, we can look at these dissections of the block. Starting at the encoder, the primary motivation for this design choice is the conditional application of dilated layers, you can see with the dotted line. Whereas the expanded receptive field will only be beneficial at certain stages of this architecture. This proved to have a significant impact on its performance through various tests and experiments we conducted. On the other hand, the decoder will follow a more simple design with a residual connection for retention of those simple features and early features, just like the unit style design. Influenced by the success of RIT-Net's combined loss function, we applied a combined loss function with generalized dice loss and categorical cross entropy. This combined loss function demonstrated a massive increase for the iris and pupil categories specifically, where both the iris and pupil had an extremely small volume of representation compared to the other class features, background sclera. We employed two different training methods to EyeSeg. First, we established our own baseline, if you will, with a standard supervised learning approach, which actually performed really well given the amount of labeled samples, yielding approximately a 94% mean intersection over union. Second, we employed a semi-supervised learning environment using pseudo labels generated highly confident predictions, as well as the provided labels. Although this training method had promising performance increases with our local testing, we unfortunately did not have access to the hidden test set for this experiment to further test and compare between these two. To make a thorough benchmark of EyeSeg, we compared the performance of EyeSeg against the provided baseline from the OpenEye dataset challenge. And we also compared it against two of the previously proposed networks from the first iteration of OpenEDS. EyeSeg overall yields a 94.5% mean intersection over union. For additional comparison, we included the other class features individually, as well as the model complexity. As seen in the results table and the figures below, EyeSeg does perform well. However, there is a degradation of performance you can see in that bottom picture, as well as you can see in the results table under the sclera category, where this is apparent to be a challenging class feature. This could be solved with some of our future works, whether that is with a memory unit such as like an LSTM, or exploring other methods of domain adaptation or self-training. I believe that incorporating sequential information could mitigate the issues that we saw in that results section of EyeSeg. But this is all I have for you, and thank you for your time.
Thank you very much for the talk. I don't know if the technical issues, I don't think the technical issues are resolved. So if there are any questions, please speak them out over text. All right. Okay, so I believe you're reading this too, Jonathan. There has been a question regarding the number of parameters being potentially a bit large relative to other architectures, I presume in relation with the OpenEye dataset challenge. I think all right. Given the circumstances, I wonder if questions could be submitted offline instead, if that's okay with you, Jonathan. I imagine it takes time to formulate your answer in text. Okay, I'll assume that's okay. apologies for the setting. There are always going to be a few technical hitches. Thanks a lot for everyone's patience in general. For now, that concludes the section with the 4 accepted papers. Congratulations once again to all of you. You are all receiving or have received a Adobe Eye Tracker. Hopefully that will be interesting towards your next hobby or research efforts. Yes, so that concludes my part. I will hand over to Sachin Talati of Facebook Reality Labs.
Yeah, thanks. Hi, everyone. I'm Sachin from Facebook Reality Lab. On the behalf of entire OpenEDS Challenge organizing team, it is my pleasure to now announce the winners for the Facebook-sponsored OpenEDS 2020 Challenge. I will do so via a pre-recorded talk, which we'll play soon. Following my talk, we will hear more about the work from the first place winners of the 2 challenges. On the behalf of Facebook Reality Labs organizing team, I'm happy to announce the winners of the Facebook-sponsored OpenEDS 2020 Challenge. Shout out to all the organizers who diligently worked in the background to make this challenge a success. The theme for OpenEDS Challenge for 2020 was spatiotemporal dynamics. In line with this theme, we hosted 2 challenges, Gaze Prediction Challenge and Sparse Semantic Segmentation Challenge. Eye tracking applications, for example, foveated rendering, can benefit from low latency gaze estimates. For foveated rendering, in particular, fast eye movements present a challenge due to the transmission and processing delays present in the eye tracking and graphical pipelines. If the pipelines do not compensate for the delays, fast eye movements can take the user gaze to areas of the image that are rendered with low quality, thus degrading the user experience. While compute efficiency is critical to solve this problem, gaze prediction can also offer a way out. If predicting future gaze location with high accuracy is feasible, it would allow for implementation of a foveated rendering method that would match closely with the human's visual acuity function. The challenge therefore calls for ideas and methods for gaze prediction from sequence of input eye images, ideally leveraging spatiotemporal nature of the problem. The second OpenEDS challenge for the year 2020 was sparse semantic segmentation of eye regions into 4 important categories: sclera, iris, pupil, and the background. The bigger picture is accurate eye segmentation improves eye gaze estimation. Eye segmentation models require labeled annotation, a cumbersome task, which contrasts with the ease with which we can collect video sequences of eye images. The question therefore remains, how can we best leverage sparse labels available on some of the images from video sequence to generalize across all images in the sequence? This challenge is aimed at solving the label propagation problem. In this slide, we present some numbers on the participation in the OpenEDS challenge. Gaze Prediction Challenge saw 13 qualified participant entries, and Sparse Segmentation Challenge saw 22 qualified participant entries. It was interesting to note that majority of the winning teams, which we will soon see, participated in both challenges, though these teams were winners only for one of the 2 challenges. And the winners for Gaze Prediction Challenge are: first place to Team Random B from Russia, represented by Anton, Skoblov, and Vladimir. Their submitted model produced a prediction error of 3.076 on the test dataset. The second place goes to Team iMazing, represented by Vivek Mittal from India. His model produced a prediction error of 3.31. And the third place winner goes to Team Dmitry Konovalov, represented by Dimitri from Australia, and his model produces prediction error of 3.34. And the winners for Sparse Semantic Segmentation Challenge are: the first place goes to Team BTS Digital from Kazakhstan, represented by Almaz and Zanseri. Their submitted model produced an accuracy of 95.17% measured in terms of the mean intersection over union metric. The second place goes to Team Tetelius from Russia, represented by Tetanikov, and their model produced an accuracy of 95.12%. And finally, the third place goes to team from United States, Team JHO, represented by Daniil and Sanchit, and their model produced an accuracy of 95.02%. Heartiest congrats to all the winners. We will reach out to each of the teams following the workshop to arrange for prize money distribution and the winning plaque. So we have the winners now. I would like to invite the first place winner of Gaze Prediction Challenge to present their work now.
Hey, my name is Anton, and I'm happy to be able to have this presentation at this workshop. My colleagues and I have won the Gaze Prediction Challenge, and in this presentation, I'll describe our solution and our ideas. Above all, we are independent researchers. We don't have experience with eye tracking, and it was our first time in this area. I'm working at I2X in Berlin as a backend engineer. Svetoslav works as a ML engineer, and he is from Voronezh, and Vladimir from Moscow, and works as senior CV engineer at Cifra. Actually, we were doing a competition in our free time. A few months before the competition, we've started to research a topic of modeling human visual attention. We've begun our research related of datasets, papers, and supplement materials. Our initial point was a database of eye movements called Hollywood video clips. Soon, we've discovered OpenEdc competition and decided to participate. Let's talk about task. The task can be formulated as follows. Given 50 gaze vectors, we had to predict 5 gaze vectors in the future. In the out-of-sample subset, history of that 50 vectors was absent, so we needed to predict them too. On the right side of the slide, you can see metrics for this competition. Our main idea was to split solution in 2 parts, the estimator and the forecaster. We wanted to avoid sequence-to-sequence solution because for us it was too hard and we thought we don't have enough time to implement it. The estimator takes one picture and predicts vector for it, and forecaster takes 50 gaze vectors and predicts the following 5. So our whole pipeline take a sequence, predict all vectors for the sequence frame by frame, predict the following 5 vectors. Let's talk about the estimator. Here our main idea was to use augmentations. Augmentations are widely used in order to extend dataset and make model prone to errors. Mostly used as color augmentations, as geometry augmentations. We didn't find any existing solutions for gaze vectors, but found for B boxes, for key points, and for our labels. And we decided to write our own solution. We took augmentations library and made a path for it. So our forks is capable to augmentate gaze vectors. You can see original frame, also augmented vector, vertical flip, and shift, scale, and rotate augmentation. Let's talk about models we used. We've tested the following models: ResNet 18, ResNet 34, MobileNet version 2, EfficientNets, different versions. And we choose ResNet 18 for our final solution. Which insights do we have? Extensive augmentations increases the score, and training works fine with careful learning rate schedule. The estimator have achieved very low error between ground truth and predicted vector. And because of the test subset, I will talk about it on the next slide. Carefully trained estimator was the key to win, on our opinion. So what's wrong with test set? We've predicted all test sequences by the good estimator and tried to explore the end of each sequence. We've made some visualizations and checked the amount of movements in the last 10 frames for every sequence. There are only 500, 600 sequences with non-static movements in the whole test subset, which contains 6,400 sequences. And we've decided to improve our estimator and keep the forecast simple. On the right side, you can see visualization of gradients between two frames for all test sequences. We have a few thoughts about data and about the metric. Looks like we need to resplit our dataset because forecast over static sequences doesn't contain a lot of meaning so far as we know. If we will add more sequence with any movements in the end of it, it will be more helpful to predict them, but not static sequences. And also our second thought about the metric. Why metric error is equal for the first and for the fifth frames of all predicted frames? It's harder to predict fifth frame than first, so maybe we have to do something here too. So what do we know now? We know that we don't need complex models for the forecaster, but in the beginning of this competition we wanted to implement this paper about eye movement prediction with Kalman filter. And also we know that improving of the estimator gives more than improving the forecaster because of test subset. And reducing error of the estimator is better for static sequences than reducing error of a forecaster. What did we try to do with the forecaster? We tried to use different methods for the forecasting, like exponential smoothing, linear regression for each sequence, rolling average, ARIMA models, recurrent nets, and other methods. In the same, we tried to make our sequence more smoothly because we predict frames, not all sequence, and juggling was a problem for us. Good point here was Savitsky-Golay filter. Visually it works fine, as you can see on the chart, but on the validation it decreased score a bit. So in our final version we don't use it, but we think it can be very useful in the real life. And on the chart you can see the estimator, the original track, and Savitsky-Golay filter for each excess for specific sequence. So our final, the forecaster solution is very simple. Check if there is movement at the end of the sequence. We calculated average gradient of the last 7 frames. If yes, we just add this gradient to the last prediction 5 times for each prediction frames. And if no, we just apply rolling average on the last 3 frames and we add new frame to the end of sequence and then recalculate average of the last 3 frames and make it 5 times. We make it for different axes separately, but we think the best decision here is to use LSTM networks. We tried one, but it was learned on the bad predictions because we used test prediction from the estimator for training our LSTM network and we didn't have enough time to retrain it. Also, it isn't so useful for the static sequences. And thank you for the competition and for your attention. I'm ready to answer any questions. Thank you again.
Thanks, Anton, for this wonderful talk. And again, congrats for being the first place winner. So folks, yeah, Anton is here. If you have any questions, please ask directly or in the chat box or Q&A. Maybe I should ask one. I found it very fascinating, your observation that we actually don't need spatiotemporal dynamics to do estimates as opposed to just doing a simple frame-by-frame estimate. And even for the forecasters, you suggested that LSTM may be a right approach, but you didn't have time. Just curiosity, I mean, if you have to make a guess and if you had sufficient time, like what type of improvements could you have seen? I mean, the bar in general is, sub 3% is what we want to get. So do you think we can achieve that?
Yeah, so I guess first of all, we can achieve also improvement by estimator because it's not the best model we have, and I guess we can improve it lower than 3 degrees. And also, I guess the good forecaster can be here too. So I guess so. All our last error on the leaderboard was about 0.05 or something like that, and we think we can decrease it to half of it, I guess. So it's absolutely open task, and I think we can improve it a lot using LSTM network. So if we will have enough time to implement it.
Okay, thanks. Do we have any other questions?
One small question. You said you use the ResNet 18 for the final architecture. Do you have any insight why you choose this architecture?
No. First of all, we tried our models with more count of parameters, but yeah, we didn't find that it will increase the score because I guess tasks by self it's very simple because we have like good data and we don't have like a large amount of parameters to learn something, and ResNet 18 was fine for us by metrics, so we tried to learn our models with more parameters, but ResNet 18 was enough. And also, I guess for us, my point was use augmentations because we tried to make more harder to learn our network compared to original data, and yeah, it worked for us.
Okay, thank you.
Okay, great. Thanks, Anton, again for your contribution. Next, we would like to invite Almaz, who are the winners for the sparse semantic segmentation challenge.
Hey everyone, my name is Almaz Inalayev.
And my name is Jansir Ikram, and we are Team BTS Digital. We are the winners of the Facebook OpenEyes Sparse Semantic Segmentation Challenge. Briefly about us, we are from Kazakhstan and both of us are computer vision engineers at the BTS Digital company. So let's get started. Our presentation consists of 5 main points. First, we are going to talk about the challenge itself, about the problem state, dataset, and what metric are we going to improve. Then we will focus on our solution, baseline, and what techniques we apply to improve our score. We will finish the presentation by summarizing the main ideas and giving further thoughts on what can be done to get better results. Before going to the main part, let's watch the timeline of the competition. The competition launched on April 11th. We started competing on the 4th of July and our baseline method was ready on the 18th, so we had a bit less than 2 weeks to make a competitive solution. The main goal was to train such a model, which takes the image of an eye taken from a VR headset as an input and generates the mask by 4 classes: background, sclera, iris, and pupil. Let's deep dive into the dataset that we are provided and analyze it. The dataset was collected from 74 unique participants and contained 200 video sequences. Each sequence has approximately 150 frames, where about 7 to 14 frames are annotated and have semantic segmentation masks. In total, we have 1,605 frames labeled out of about 29.5 thousand frames. Each image has size 400 to 640 pixels. Since the dataset is hand-annotated, there are always little mistakes, especially in segmentation tasks. Mostly, we faced this issue for the sclera class. For instance, this frame is missing some sclera class, which was mislabeled as background. One more example is, if to compare 2 neighboring frames, they are labeled differently. Taking these points into account, we conclude that mislabeling is one of the reasons why sclera was the most difficult class to obtain. Say we have ground truth mask A and predicted mask B. The score taken by the intersection area of this mask divided by their union gives us intersection over union score. The competition score was mean IOU, which is the average of IOUs of 4 aforementioned classes. So let's jump to the solution. As stated before, the labeled images are only 5.5% of the total, so the augmentation is crucial. We used the augmentations library to enrich our dataset. Since the sequences were captured from the static VR headset, we decided not to use aggressive augmentations. The heaviest one was the grid distortion, which narrows or widens the eye and creates a new set of unique images. For the baseline, we used unit architecture and took the SeriesNext 50 pre-trained ImageNet model as its backbone. To evaluate our model, we used a 10-fold cross-validation across video sequence. We set 8MW as the optimizer, and for the loss we took a combination of focal, dice, and binary cross-entropy losses with equal weights. Starting from 0.003, we updated the learning rate by multiplying it by 0.5 every 20 epochs, and trained our network approximately for 100 epochs. At the end of the day, our local score was equal to 0.9453, and leaderboard gave us 0.9458. So our baseline is ready, and the local validation correlates with leaderboard. After, we started playing around with the different backbones. As you can see from the tables, the efficient nets family was the highest scoring backbones. By the way, fold 1 was the worst, so we jumped to fold 2. As mentioned before, the Sclero class is the hardest one to predict. Before 2 days to the deadline, we made a visualization of our predictions, and noticed that our model mostly made mistakes on the borders. We assumed it's because of the crop augmentations, so we decided to remove them. As you can see, the score improved after removing the crop augmentations. However, we had only one submission left, so we started training fold 3 without crop and got the highest results than all models that we trained before on the local validation. Now my teammate Almaz will discuss strong techniques we used in this competition.
One technique that came in handy in this challenge was pseudo-labeling. Pseudo-labeling is applicable when there is a lot of unlabeled data, and since 95% of the dataset was not annotated, we use this approach to boost our scores. Firstly, we train our model on labeled data as usual. Once the training converges, we use the trained model to predict the sort of ground truth labels for unlabeled data, and therefore obtain pseudo-labels. After that, we use both labeled data and pseudo-labeled data to train a new model from scratch. This allows us to train on 95% previously unused data. In most of the pseudo-labeling approaches, there is a filtering step that removes bad predictions. We want to train only on our most confident predictions so that uncertain cases will not be reinforced in further training. Choosing high-quality predictions for the classification task, for example, is fairly easy since there is only one value to look at. However, the segmentation task has hundreds of thousands of these values. It's not so straightforward to filter poor samples from good ones. We've tried multiple techniques for filtering the pseudo-labels, but interestingly, using the raw pseudo-labels without any filtration worked better for us. Another thing to notice, the pseudo-labels should be obtained from an ensemble of models instead of a single model. One of the reasons is that individual models can have their own bias, and if used alone, the bias can be propagated into the dataset. Another reason is the ensembles always work better than standalone models, so you're simply getting better labels. Here are other minor details of our pseudo-label training. Firstly, we used hard labels, which is simply an argmax over the predictions. We want to try training on soft labels, which are raw softmaxed logits from the model, but we didn't have time for experiments. Secondly, no ensembling over different faults is allowed, since this would lead to leakage and our validation scheme would be compromised. Finally, models were trained from scratch each time, instead of fine-tuning previously trained models, to avoid bias propagation that could be introduced by those models. Here are the results of pseudo-labeling. As you can see, on average there is a 0.2% improvement compared to training only on labeled data. Another de facto standard technique always used in competitions is an ensembling. we've tried multiple ensembling techniques. So here is the raw logits output from one model. Class cores are located horizontally and the pixels are shown vertically. It is not recommended to average models' outputs on this level because each model can carry its own bias with different distribution. Usually, those outputs are run through softmax function to normalize the logits and then summed over all models and renormalized back again. Another ensembling technique is temperature shaping. It is similar to the softmax function, except the outputs are additionally taken to the power of 0.5. In a sense, such an ensembling technique enhances the distribution over classes by reducing variance. Interestingly, in our practice, the best performing ensembling technique was average across raw logits. This could be explained by the fact that we used only efficient net family of models. Some additional info about our ensembling is the following. We used flips along the x-axis. Also, we did weighted averaging so that better performing models would contribute more. And in total, our best submission consists of an ensemble of 10 models trained on 3 folds. Here are the results of our ensembling on local localization. And if you look closely, you can see that we can get a consistent gain of 0.1%. Using all of the techniques described, we were able to get the first place in the competition. However, we believe that given time, we would be able to get even better scores. Also, the code will be published at the following link. As I said earlier, we believe that there is still plenty of room for improvement. Simply training on all folds with our best pipeline could easily boost our score. Also, more rounds of pseudo labeling could potentially increase the score too. Another thing that might be helpful is using soft labels for pseudo labels in combination with label smoothing on ground truth data, which usually works best when annotations are noisy. Finally, a minor thing we haven't tried was fine-tuning the weights of the loss functions. This is pretty much it. We are happy to answer your questions if you have any.
Good day, everyone.
Yeah.
Hi. Was fine-tuning the weights
for a very nice talk. So yeah, we want to open the floor for questions. Okay, just one question I have is, so the pseudo labeling technique and the ensembling technique that you used to boost scores gave an improvement of 0.2 and 0.1, if I heard correctly, percent. Although so what that tells me is that just using 1600 trained images, you were pretty much capturing the significant portion of the accurate scores. Any thoughts on like what that says about the data quality? In other words, were there a lot of correlations in the sequence that you think contributed to significant gains just obtained by using unlabeled data?
Yeah, so the thing about this data set particularly is that all of the images are captured from the VR headset, right? And in a sense, there is a lot less of a variance between any two samples. So I think that contributed a lot. So additional annotation or pseudo labeling did not contribute as much as it does in other tasks, for example, let's say COCO dataset, right? And therefore, there were like very, very minor improvements, 0.1, 0.2%. And also, I think the segmentation task annotation is very hard thing to do because there is not always a consensus between two people regarding if this pixel, for example, is a class of sclera or a class of iris, for example, right? And this kind of thing also might make it harder for the model to train. And if we see the scores across classes, we can see that most of the classes actually
are performing very, very well, except for the square class, which is very challenging thing to annotate. Yeah, so I think that the 5% of data that was annotated is pretty much enough to get very good working solution that could be applied in the industry. Yeah, I think.
Well, thanks, thank you. There's one chat box. There's one question in chat by Sanchit. Was the 0.02 gain just by pseudo labeling or individual folds, or the final ensemble on the leaderboard?
Yeah, so it was on the individual folds. So for example, we have we get pseudo labels from an ensemble of, for example, 3 models, and then train the pseudo labeled new model, and then we see how it scores actually, and we see that 0.02% of gain. Yeah, so it's on individual folds.
One more question. Did you measure the effect on the ensemble on the test set?
So actually we did. That was one of the first things we tried, and we were getting really good results. For example, in our first baseline model, we submitted only one model, and then it was scoring 94.59, I think. And then we assembled 3 models, and we were getting closer to 95%. So yeah, the good thing about the competition was that the test set was very well correlated with our local data set, local validation scheme.
Okay. Sorry.
Okay.
We had another correction. So no, I meant impact of pseudo labeling on test set.
I see. So yeah, we did measure that. We didn't do it fully because we didn't have a lot of submits. We were doing it to the end of this competition. But yeah, pseudo labeling was adding 0.02, 0.03%. Yeah. As I said, the local score and the test score were correlated, so pretty much they're interchangeable. Thank you. Thank you very much. Thank you for the competition. It was very interesting. Hope.
Cool. I think that's great. So thanks again to all the participants and the winners. And with this, I think we are done with the first part of the workshop. The second part will be at a more reasonable time for folks in the United States. So see you then.
It will be for approximately like 8 hours later. Yeah. Okay. Thank you all, and see you later.
Bye.
Bye.
Goodbye.